Hello everybody and welcome back to my channel. This tutorial is a continuation on analyzing beams and drawing shear force and bending moment diagrams. This is the third example on this topic. You can check out the first and second example from the links on the description of this tutorial. Let's get right into the example. As you can see on the page, we have a simply supported beam with a 30 kN force to the left point load of support B and two uniformly distributed loads of 20 kN per meter and 35 kN per meter, spanning distances of 4 meters and 3 meters respectively. Let's start by calculating the reactions so that we can draw the shear force and bending moment diagrams. We shall start, say, summation of moments due to the support B should be equal to 0, meaning total clockwise moments should be equal to total anti-clockwise moments. We shall say take the total load for the UDN, the first UDN, those are the forces that are going to cause the anti-clockwise moment, So we shall take 20 times 4, which is equal to 80, times half the span of the distance is 2, plus 35 times 3 is 105, times half the span plus the distance from B to C, that shall give us 5.5 meters, should be equal to the support reaction RD times the distance from the support B to D, that is 7 meters, plus 30 times 2. Do note that this force 30 is going to cause an anti-clockwise moment due to support B. Doing this, we shall get 160 plus 577.5 should be equal to 7 RD plus 60. When we add this together, we shall get 737.5 kilonewtons meters should be equal to 7 RD plus 60 kilonewton meter. Take this 60 to the other side, we shall have 737.5 minus 60 to be equal to 7 RD. Doing that calculation, we get 677.5 kilonewton meters is equal to 7 RD. RD will be given by 677.5 divided by 7, which shall give us 96.79 kilonewtons. With that done, we can now get the reaction for support B by using the second equation of static equilibrium, which states summation of forces along the y-axis should be equal to 0, meaning total upward forces should be equal to total downward forces. So the upward forces are going to be RB, the reaction force RB, plus the reaction force RD, that is 96.79 kilonewton, should be equal to the total load, the total downward forces, that is 30 plus 80 plus 105. Adding this, we get 215. We have 215. RB plus 96.79 is equal to 215 kilonewtons. Therefore, RB is equal to 215 minus 96.79. RB will be equal to 118.21 kilonewtons. with the reactions done, we can go ahead and start drawing the shear force diagram. I'm going to show you how I came about with my diagram. We start from the left edge, this side. On this side, we have a 30 kilonewton load, so we'll start from zero. From zero, go downward 30. So the force of negative 30 is going to travel parallel to the zero line up to this point it reaches. It intersects the support B, where it's going to encounter a reaction force of positive 118.21. We shall add negative 30 plus 118.21 to get to 88.21, because we are moving upward. That is a positive force. That is why we are going upward. At this point, we encounter this uniformly distributed load of 80 kilonewtons. The distribution is 20 kilonewton per meter, but the total load is 80 kilonewton. So we shall take 20 times 4 to get 80, then subtract it from 88, which shall bring us here to 8.21. That is this point here, right? Then at this stage, we encounter, at point C, we encounter another uniformly distributed load of 35 kilonewton per meter spanning a distance of 3 meters. So you multiply that to get 105, then subtract 8.21 minus 105, which shall bring you back to negative 96.79. This is on the negative side. So show this side is negative, this side is also negative, but this upper part is positive. So at this point D, remember we found our reaction force was 96.79 for RD, reaction force at D. So we take negative 96.79 plus 96.79, which is going to bring us back to zero. With this done, we know that our calculations for the reactions are right. We can now go ahead and draw the bending moment diagram. To draw the bending moment diagram, we usually find the area of the shear force diagram. So just start from the left hand side also again. So we have, since our shear force diagram for the section AB is on the negative side, you also have to plot it on the negative side of the bending moment diagram. Do note that the negative side of our bending moment diagram is usually the upper part, and this lower part is usually the positive side for our bending moment diagram. So we shall take negative 30 times 2 meters. That shall give us 60 kilonewton meters. So you plot the 60 kilonewton somewhere up here, then join using a slanting line. Then we come to the section BC. For section BC, we calculate the area of this trapezium, which is half height into A plus B. So our height is 4 meters, A is 88.21 and B is 8.21. So if you calculate that area, you get let me do the calculation first, then I give you the answer. 88.21 plus 8.21. You get 192.84. So with 192.84, remember we are on the positive side of our shear force diagram, but we want to take this side on the positive side of our bending moment diagram. We shall take negative 60 minus 192.84. No, sorry, plus 192.84 shall take us to 132 0.84 kilonewton. That is this point here. To draw this, usually you draw this using a curved line that is convex in nature. Yeah, convex in nature. So at that point, we now go for the section CB, C to D. But before we go to that, you have this smaller section here, C, this section, C to C prime. I'm calling this C prime because that is just a small distance. We have, remember the total load we had here was 105 kilonewton. That is from C to D for the section on the shear force diagram. So we shall take, say, if 105 kilonewton is equivalent to 3 meters, therefore 8.2 kilonewton will be 8.221 times 3 divided by 105. That is going to give us 0.23 meters. So this distance here is 0.23 meters. So we shall have to find the area of this small section that is triangular in nature. We shall take half, that is 0.5, times base, which is 0.23, times the height, 8.21. We get 0.94. That 0.94, you add it to the 132.84, this 132 here, because you are still on the positive side. So we continue going back on the positive side of our bending moment diagram. So we take 132.84 plus 0.94, which shall give us 133.78 kilonewton meters. That is this point. That one also, you draw it using the curved line. It's convex in nature from the top. Yeah, and we are now from the section. We now get the area of this section C prime to D for the shear force diagram. To get this distance from here to here, we subtract 3 from 0.23, which gives us 2.77 meters. Then you get the area, 0.5 times 2.77 times 96.79. That gives us 134.05. So remember, we are on the negative side of our shear force diagram for the section C prime to D. But in our bending moment diagram, we are on the positive side. So we want to go back to the negative. So we shall take 133.94 minus 134.05, sorry, 0.05, to give us 0.11. Sorry, yeah, we should have 0.11 kilonewton meters. So with this done, we have reached the final stage of our drawing, and with this you can get the maximum marks for the question, and unless you are asked only to calculate the point of contraflexure, which is this point here, the point where the bending moment diagram changes from negative to positive or positive to negative. And that is a video for another day. Thank you for watching. Please remember to like the video and share it with your colleagues, and remember to subscribe and comment if the video has been useful to you. Thank you.